Hello and welcome. This is Chapter 8, Section 3 on circular orbits. And this is a topic that certainly has much more detail in Chapter 13 on Newton's theory of gravity. Yet it's very helpful to just reason about this and to get kind of a preparatory sense of orbit. And so we have here a classic example. Sometimes it's called Newton's Canon. We always have these abstract kind of fictitious thought experiments named after famous scientists to illustrate a concept. And so we got a planet. It doesn't rotate. It doesn't have any atmosphere. For all we know, it might be hollow out on the inside. It doesn't matter. But what does matter is that there's a tower of height h, and the people on planet whatever are launching a cannon. And so obviously what happens is when the speed of the cannon, launch speed of the cannon is small, and by small, by earthly standards, less than 100 miles an hour or so, the trajectory of it is a parabola, right? And so that's what we've got here. And we call this the flat Earth approximation. The flat Earth approximation will be given much more consideration in Chapter 10 and 13. So yeah, that's what happens as you get further away, as the launch speed, as the initial speed v0 is increased, it starts to resemble less a parabola and more a kind of a strange mixture of a parabola and a circle. I don't think it has a specific name, but it's neither, and it's kind of mixed between one. So evidently a parabola at that flat Earth has a small, very, very sharp curvature. And then, as it gets further out, it's constantly falling, and you can visualize this, that it's kind of falling towards the Earth. And then eventually you can imagine there's a just optimal speed. Again, this is two-dimensional, an optimal speed where it's always falling, and it reaches back and it's falling at a rate equal to the curvature of the Earth, so to speak. And so this is called orbit. Now, a couple of realistic remarks about orbit. An object would certainly not orbit in the atmosphere, because those drag forces would be so large that it would incinerate, because as you'll learn in thermodynamics, drag forces increase the temperature of those objects. That's why we have heat shields for the space shuttle upon reentry, for instance. And also another remark is that, so there is just like the optimal speed for the banked curves, there's an optimal specific speed to orbit a planet at a certain altitude. And we actually don't usually talk about altitude. We talk about radial distance, the distance of orbit from the object to the center of the planet, or the center of the Earth. So this is certainly a good application of dynamics in a plane, because, as you know, the gravity on a flat surface kind of points towards the ground, so it's vertically downward. But as you extend that picture, you find that it's actually more, gravity is actually directed towards the center of the Earth and not necessarily vertically downward. And so we say that the force causing the centripetal acceleration is mg, as usual, but now that's directed inward. And now that gives us a way to analyze this with circular motion. So what are some calculations that you can do with this object? Again, this is a spherical planet that doesn't rotate, and there's no atmosphere. Each one of those assumptions adds a complexity to this discussion. For instance, the Earth has what's called the equatorial bulge. So the equator, distance from the equator to the center, is about 10 or 15 miles bigger than the distance from the center to the top or the bottom. And rotation, as we'll see in a minute, does also have an effect. But what we've got is that the acceleration towards the center is actually g towards the center. And so what is the velocity then of an object? Well, we have v squared, velocity of the object squared equals the radius times g. And so we can solve that for v to get an expression for the radius. Would be square root of rg, right? Doing that simple calculation, but typically, yeah, velocity of orbit being square root of rg. And so that means that no matter what the size of the object, you don't see the mass. The mass of the object does not come into the velocity. You can have satellites of any size and shape at the same altitude and all orbit with the same speed. That's why the asteroid belt is stable. The asteroid belt is stable because you have little pebbles, all, rocks from the size of little pebbles all the way to rocks up to the size of small dwarf planets, all peacefully coexisting and orbiting at roughly the same radius with the same speed. So they don't ever really run into each other. And then if we take this a step further, we can find an expression for the period of orbit. The period of orbit is just related to the velocity by 2 pi r over v. So we have a square root of rg, but then we got this square root rg on the bottom. If you look at this equation here, you got t equals 2 pi r over the square root rg. And so we're able to get an estimation for the period of orbit being equal to the square root of the radius. Again, this is the distance from the center of the planet to the point of orbit. This is a great introduction to these types of problems. Certainly in chapter 13, we discuss it in much more detail because as we find out in chapter 13, g itself changes with altitude. And so g for a lot of these orbiting satellites won't necessarily be 9.8. And sure enough, for like long-range communication satellites, g's hovering probably around somewhere between 6 and 7. For the moon, it's like 0.002. So it gets very, very small the further you get out. But that's a detail we'll leave for chapter 13. But this is certainly a good introduction to circular orbits. The key takeaway is that gravity is the force producing the centripetal acceleration for a particle in circular orbit. We talk much more about this, and including elliptical orbits, in chapter 13. But for now, that's the end of this video. We'll move on to reasoning about circular motion. A very fun topic in the next section. So thanks for your time. We'll see you back here for the next one. Take care.